All right, first off, I have to apologize. I don't have the sheet in front of me to have a picture on here. You're lucky I'm doing this at all. I left my iPad at school and I'm borrowing my wife's, so I don't have any stuff with me other than the solutions online, so I'll work from there. So I'm going to have to read the questions and kind of explain it without having as much of the details in terms of pictures and text. So the first question, when a box rests on a round sheet of wood on the ground, it exerts an average pressure P on the wood. So P is the pressure. If the wood is replaced by a sheet that has half the diameter, what is the new average pressure? So half the diameter affects the area. The pressure comes from force over area. So P is inversely proportional to area, but area is proportional to the radius or the diameter squared. So what you're basically doing by halving the diameter is you're quartering the area. If you quarter the area, the pressure will be 1 over 1/4 or 4 times as much. So the new pressure would be 4P. All right, next question. As shown in the figure, fluid fills a container having several sections. They want to know at which point is the pressure the greatest. This is a trick question. A, B, C, D are all at the same depth, and it doesn't matter what the shape of the water is above it. If it's that, I don't know what the heck the shape has to be. I mean, they have all different weird ones, squares, diagonals. They're all at this same depth here. So the pressure is the height of the fluid above it, not the shape of the fluid above it. So the answer to that one is E. Next question, a plastic block of dimensions 2 centimeters by 3 centimeters by 4 centimeters has a mass of 30 grams. What's its density? Probably shouldn't even do this one. Density is mass over volume. The issue is it's in grams per, actually it's grams per centimeter cubed, so we can leave everything the way it is. It's 30 grams divided by 2 by 3 by 4. I don't have a calculator with me, so I'm probably not going to do many of these out, but that's 10 over 8, so whatever that is, 1.25. So next question. Number 4, the Aswan High Dam on the Nile River in Egypt is 111 meters high. What is the gauge pressure? Gauge pressure refers to, so if we look at it, P absolute equals P naught plus rho GH. Some people were confused. They thought gauge pressure was P absolute minus P naught, and they're not wrong. But what does that also equal to? Rho GH. So that's the information you have in this question. So you use rho of water, 1,000 kilograms per meter cubed, G 9.8, and H was 111 meters. You do that out, you get the answer is A. Okay. Next question. Boy, we're zipping right through this. 3 minutes. Number 5, what force does the water exert in addition to that due to atmospheric pressure on a so first of all, your submarine is submerged, underwater, but they want you to include P atmosphere. So the pressure at this depth here, P at, let's call this point A, P at A is P atmosphere plus rho GH. Rho GH, they give you the seawater, rho, G we know, and the depth is 9,400. So we should be able to find that quantity just fine. Plug in 101,300 pascals. Don't put it in kilopascals, or at least don't do the calculation down here with it in kilopascals. Convert it to pascals. So you'll find P. And then if you want to know the force, pressure is defined as force per area. Just cross multiply, and the force is pressure times area. And in this case, it's a window with a radius of 44 centimeters, so just change it to 0.44 meters and do pi squared. Sorry, I screwed up where the decimal point was. You do that, and I believe you get answer D. All right. I'm going to move on to the next page. Number 6. I did this in one of the classes today. The key here, and if you check my answers online, I'll try and redraw it quickly here. Looks something like this. Pick this point here. There's some oil here and some other fluid here. The key is if this is in equilibrium and it's, I guess they're both open, whoops, they're both open to the air, this point, the pressure is going to be the same here as it is here. If it wasn't, the fluid would be moving, right? This would be flowing this way or this way, depending on which had a higher pressure, which side. So the fact that they're at the same pressure, I labeled it B and D over here. Whoops, D. So P at B equals P at D. So I said rho G H where D is equals rho G H where B is. Now the rhos are different. This is the rho of this, I think it was oil. So you would plug that in, and this rho is the unknown fluid over here. So once you do that, you see that P of the unknown, the G's cancel out, is equal to rho of the oil. Excuse me, I might have said P, I meant rho. H at B and H at D, and that H is the height of the height of the fluid above it. So it would be 20 centimeters divided by 5 centimeters. So it's 4 to 1. 4 times the oil, when the oil's rho was 900, is 3,600 if you really wanted an answer. All right, the next question. This is number 7. Hydraulic garage lift. The small piston has a radius of 5 centimeters and the large piston has a radius of 15. So you have a small piston, a large piston. This one's 15, this is 5 centimeters is the radius. So whatever. You guys can draw your own pictures pretty quickly. What force must be applied on the small piston, so the force here, in order to lift a car weighing 20,000 newtons? So this is our F2, this is our F1. We can find A1 and we can find A2 from pi r squared. Not a big deal. And then you use Pascal's principle, Pascal's law, where it's the pressures are equal in these closed systems. So we say F1 over A1 equals F2 over A2. You know, do the math, figure out what F1 is. I got 2.2 times 10 to the 3. Now the drawback here is you're not getting something for nothing. Just as a side note, this force is going to be lower on this side because it's got the smaller area, but the distance that you have to push this is going to be much smaller than the distance output you get. So you're getting this force multiplication of a factor of whatever it ends up being. Basically the A2 to A1 tells you the force multiplication, if you see that here. But that force multiplication is the inverse of the distance multiplication. So D2 over D1 is the exact opposite of that, because you don't get something for nothing and energy is conserved. Next question is number 8. A 4-cylinder cylinder of solid iron is supported by a string. So a cylinder supported by a string, so there's tension upward while it's submerged in water. So it's submerged, so there's some Fg, there's also Fp. What is the tension in the string? The density of iron is that, and of water is 1,000 kilograms per meter cubed. So it's basically Newton's second law. So we have Fb plus P are both up, or down from Fb. So if we're solving for the tension in the string, it's the weight, which is mg, and we're given on 4 minus 2. And you can probably think of it in pretty simple, just looking at it. The tension is equal to the difference in the weight, and the bearing force is equal to make it float, but it's not enough because this is iron. All right, next question. Again, double check the answers on the scan that's online on Class.
Number 9. What buoyant force does a 26 kilogram solid gold crown experience when it's immersed in water?
The density is this, and the rod of water is that. So again, the buoyant force equals Fg.
So how do we find v of the crown? You plug that in there, multiply by 1,000 kilograms per meter cubed, multiply by 9.8. So for my answer, I got 0.305. A couple more and then we'll plug this or stop it and say
Number 10, rectangular box of negligible mass, 5 meters long, 1 wide, half meter high. How many kilograms of mass can be loaded onto the box before it sinks in a lake? So when it sinks, this box is, let's see, I don't know what that's doing, 5 meters long, 1 meter wide. I don't know what I'm drawing here. Let me start over. Clear this. 0.5 meters high, 1 meter wide, that's 1, and 5 meters long. Does that make sense? 0.5. I think that's the drawing that I want. And the question is, how many kilograms of mass can be loaded onto the top of it before it sinks? So this is another one of those things that we talked about in class where you want to look at the sort of the limit. When it sinks is the moment that it starts to sink is the moment that it's completely submerged but not sinking. So you want to think of it as the water level is right there, right on top of it. So at that point we have Fg and Fb are equal. Now you're putting these masses on top of this to try and make it sink. They don't affect the volume of the water that's displaced. This is just a free body diagram. So the buoyant force is equal to rho Vg. What we're going to plug in for V is the entire volume of this rectangular box. So it's just 0.5 times 1 times 5, which is 2.5 meters cubed. Rho is of water, so that's 1,000 kilograms per meter cubed, and G is 9.8. So we get a number for what FB is. What we have to do is figure out what the mass is that equals that. Trying to look to see, do they give us the mass of the box? Oh, they don't. They say it's negligible mass. So really the Fg is just coming from the mass that you're loading onto it. So basically whatever number you get here for the buoyant force, just cancel the g's. Probably should have done that beforehand, and I think the mass is going to be 2,500 kilograms, which is answer C. Almost done. We're up to 15 minutes. This is taking a lot longer than I wanted it to, but I have nothing better to do, right, people? Sorry, that was directed at my second period class that nobody finished either of these, and they expect me to spoon feed this to you via osmosis. Never mind. Stop talking. Number 11. 1 meter cubed object floats in water with 20% of its volume above the water line. So you have 20% above. I don't know why I'm drawing as a rectangular prism, but whatever. This is 20%. That means it's 80% submerged. What does the object weigh out of the water? The density of the water is 1,000 kilograms per meter cubed. So if it's floating right now, Fg and Fb are equal. That's what floating means. Okay, so what you can gather from this, actually I probably should have done this right away, but this is good to think about. Specific gravity tells you the percent that is submerged, or the fraction that's submerged. So this tells me that the rho of this object divided by the rho of water is 0.8. If it's 0.8, that equals rho of the object divided by 1,000. That's the rho of water. Tells me the rho of the object is 800 kilograms per meter cubed. If I want to know what it weighs out of the water, I have to find the mass. The mass I get from rho v. There's rho. V was 1 meter cubed, so that's pretty easy. It's 800 kilograms. I multiply it by 9.8, and I get what looks like D, 7840. All right, that's it for the first 2 pages. You're welcome.